Hey everyone, welcome back to another topic revision video for complex numbers. Today we're going to talk about the loci. Now, before we dive deeper into the loci about the circles and line, there's one concept that we need to revisit, and that is, what does it mean by this expression? What does it mean? It simply means a vector going from z1 to z. Visually, that's what it looks like. So if you draw an Argand diagram, of two complex numbers, for example, one is this one, the other is, let's say, this one. So the z minus, for example, this is your z and this is your z1. So z minus z1 will actually be this particular vector. But z minus z1 will itself be its own complex numbers. So how will we represent that one? That one would be just simply starting from origin. So this is your z minus z1, its own complex number. That means it will have its own argument with the positive real axis and its own magnitude. So that means the magnitude, this will be the magnitude of z minus z1, and this will be the argument of z minus z1. Okay. Furthermore, when we just simply do z, for example, equals to 5, for example, like this, we basically means this is from 0. Okay, so basically means this is from 0. It's originating from 0. Its tail is at 0. So we can say tail at origin. Furthermore, this usage over here, minus z1, means that if we split z1 into some specific complex number, how this would look like. So if z1 is some specific a plus bi, this z minus z1 would look like, for example, z minus a plus bi. Okay, this could also be written as z minus a minus bi. So the signs we have to be very careful about. Alright, so when we see z minus something, for example, that would mean, if we see z minus 5 plus 3i, basically means we're talking about z minus 5 minus 3i. That means the tail of that vector is over here. The vector is originating from this. Okay, so 5 comma minus 3 would be the tail of that vector. Okay. Now let's see the three key ideas that are in our syllabus. I will explain them, I will write them first and then I will explain them also. So the loci ideas that are in our syllabus, the first one is z minus z1 equals to some constant a. Second one, z minus z1 equals to some z minus z2. And 3, that was the argument of z minus z1. equals to some angle. And the angle, we usually use the radians. Now, for simplicity, I have used equality, but these could be inequalities also. Could be inequalities also. The most likely they will be inequalities, because the past paper questions that we will see, most likely they will be inequalities. So let's see one by one what that means, and we'll do some mathematical working also to show the reasoning behind that. So for example, we start with the first one, that is the z minus z1 equals to some a, which is where a is some constant. So this is the most easy one. This is the most easy one. So what we do is we start by saying z is some x plus yi, and z1 is some, let's say for example, p plus qi. Okay, so z minus z1, that would become x minus p plus y minus q I, right? So the mod of a complex number, remember, how do we do that? Is just like mod, like if we do the mod square, remember, square of the real part plus the square of the imaginary part. And since this is equal to some constant a, this is equal to a square. Now, this form is easily recognizable. This form is easily recognizable. Why? Because this is an equation of a circle. Circle with center P and Q and radius, that constant I. Sorry. So that would mean, for example, you have z minus 5 plus 3i equals to 2, right? So if we convert this into the equation of a circle, so first off, remember that this sign convention over here, so this is like this, equals to 2, and this is your center of the circle. Okay, so how would we finish this, right? Or how would we do that? So center is 5 comma minus 3 and radius is equal to 2. So equation of circle would be x minus 5 whole squared plus y plus 3 whole squared is equal to 4, because 2 squared. And we can sketch this also now. Similarly, if this was z minus 5 plus 3i less than equal to 2. So the boundary would still be the equation of the circle, but region shaded would be all inside the circle. So region shaded, all inside circle. So let's see what that means. For example, we'll just draw this Argand diagram. So this was 5 minus 3. So 1, 2, 3, 4, 5 and 1, 2, 3, right? And the radius was 2. So that means the maximum point is over here, minimum point over here, and this would be boxed in over here, and right at 7. Okay, so we just need to draw a circle. Right. Okay, so now let's adjust it. So somewhat, yeah, so somewhat like this. Okay, so now we can delete these guiding lines. We can keep them also, doesn't really matter. So this is your 5 and this is your minus 3. Now, if this is less than equal to 2, we would shade all the region under it. That would be the answer for this. Now, in questions like this, there's a common line of questioning that you will see in the Loci questions. That is often going to be the greatest or smallest. Two things, either argument of z that satisfies the shaded part or the loci or locus of z, or some mod of z. Oftentimes, very rarely, not often, occasionally we will see finding the z also. Finding z corresponding to these two also. So greatest value of argument z, smallest value of mod z. Alright. So let's look at a few examples for circles with simple conditions, and we'll see how to deal with these type of questions. Okay, so let's see this. The complex number u is given by this, right? Without using a calculator to find the two square roots. Square roots we have already done in the previous video. We'll see this one. On an Argand diagram, sketch the locus of the points representing complex number z satisfying the relationship z minus u is equal to 1. Determine the greatest value of argument z for points on this locus. Alright, so that's what we need. So basically this, the center of the circle, see this is a center, this is a circle of radius 1. So this is a circle of center minus 1 and 4 root 3, radius 1. Okay, so just to like have 4 root 3 over there, 4 root 3 is almost 7 basically. Okay, and radius is 1, right? So we just need basic sketch over there, basic sketch. Since this is at minus 1, its one side will be touching the y-axis, so remember this. So somewhere over here. Okay, we'll make it like this. It doesn't have to be very accurate, but I just wanted to have the center somewhat like this. Right, okay. So for example, this is your minus 1. I know it's not perfect, but it doesn't have to be perfect. So this is your imaginary axis, this is your positive real axis, this is your center. Okay, so this is your center, this is roughly your 4 root 3. See, I'm not using the correct scaling like in the same way. as I was doing over here. And so this one would be 4 root 3 plus 1, and this one would be 4 root 3 minus 1, and there's a whole scaling that we did not bother to do that. So for example, this could be over here. Alright, so not drawn to scale basically. Now, determine the greatest value. So equals to 1, that means this is the circle. Greatest value of argument z for points on this locus. So 1 point, argument z, remember what argument z means, argument z minus 0. Alright, from the origin. So either you have this point, where you're actually, if you draw a line from the origin, where will it touch the circle? 1 point is your tangent over here, and the other would be like this. So obviously the origin one does not count, so like we can see that this is not going to be the greatest argument, because the greatest argument would be this one. So we need to figure out what would be the argument of this. So to find this, we just have to use simple geometric properties, nothing more, nothing more. So we use the circle theorem that this is perpendicular. That means there could also be a line like this joining the circle, like this. So rather than finding the full angle, we can split the angle into 2 parts. One is this part and the other being this part. Okay, now both of them we can easily find out. Why we can find out? Because we know the distance. We can find out the distance from the origin to the center, this thing, right? So distance you can find out from the center, right? Distance to the center from origin to minus 1 4 root 3 is just simply 1 squared plus 16 times by 3, 48, 49, so that would be 7. That means this length is 7. We know the radius to be 1, so we can find out this particular angle. So theta would be sine inverse of 1 over 7. We'll keep it as it is for a moment. We'll keep the exact value for a moment, yes. Now, furthermore, we also need this particular angle. Let's call it gamma. So we have a complex number over here, minus 1 plus 4 root 3i. If we can find out the argument of this one, once again, we will just simply employ trigonometry. Simple trigonometry, nothing more. Simple trigonometry. So, sorry, this is supposed to be over here. Okay. So you can use this particular triangle also, like 7 and 4 root 3. No, sorry. Yeah, technically yes. So what I meant was 4 root 3 is the height, right? 4 root 3 is the height. Hypotenuse is 7. So that way, which angle we are getting? That way we will get particularly this angle. So you can subtract that from 180 also, pi. So different methods to do this. Easiest one is to find the argument of minus 1 4 root 3. So the argument of minus 1 plus 4 root 3i is tan inverse of 4 root 3 over 1. It should be minus 1 or 1 because tan is negative in the second quadrant, so it should be negative 1. So we need the radians. So tan inverse of 4 square root 3 right, okay, so basically I found the positive value. So the positive value basically means this thing. So we just need pi minus that. So pi minus this, pi minus this value is this thing. So pi minus tan inverse of 4 root 3. Okay, so the greatest value of argument z would just be the sum. Greatest argument z would be just the sum of these two. So sine inverse of 1 over 7 plus pi minus tan inverse of 4 root 3. And how did we actually need to give it? Right, so greatest value is given like this. So plus sine inverse of 1 over 7. 1 over 7. So 1 divided by 7. So you get 1.858. 86 you can say radians. Alright, let's see one more. Alright, so let's see this one. Okay, we don't need the A part now, okay. On a sketch of an Argand diagram, shade the region whose points represent complex numbers satisfying this. This is a circle. And imaginary z greater than 3 basically means y value greater than 3. So, first off, we just need to define this. This is z plus 1 minus 3i equals to 1. It's a circle of radius 1 and center. Remember the opposite sign. So basically this is z minus 1 plus 3i equals to 1. So center would be minus 1 and 3. Okay, so you can have a Cartesian equation for circle also. So let's sketch this out. So minus 1 plus 3i, once again the radius is 1. So 1, 2, 3. If this is 3, for example, 1, 2, 3, 4, and 1, 2, 3, 1, 2, 3. Okay. So we need the circle to have a radius of 1. Oh, sorry, my bad. So the center is minus 1, 3i. So minus 1, 3i is over here. Radius is 1. So this would look like this. Right, exactly like this. Okay, so this is a circle of radius 1, center minus 1 plus 3i. This is your 3. So this is 4 and this is 2. This is minus 1. Okay. And imaginary z greater than 3 would mean that we are we need a line like this, and we'll be shading greater than that. Now, circle this part alone means that if, for example, we just keep it separate for a minute, less than equal to 1 means all the area shaded in between the circle. And if we bring this thing over here, where all the region greater than the line should be shaded, this means the only area that we need to worry about or we need to shade is, let's shade it a different color with this part. This is your region. Now, we'll name these also. This is your imaginary z equals to 3, and this is your circle. Right, okay. Now the second part is determine the difference between the greatest and the least values of the argument z for points lying in this region. Okay, so argument z once again means measured from the origin, measured from 0, minus 0, 1. So we basically need a line coming from the origin. This is going to be the minimum. This is going to be the maximum. Okay, so in short, we need the locations of this and this. This one is easy. This is 90 degrees. This is 90 degrees. But we need to find out this one by any means necessary. And we also have this coordinate also because we had the equation. So this is, since the radius was radius was 1, so this coordinate is minus 2, 3. So it's not that difficult to determine its angle. You can use any kind of trigonometry to figure out the angle. Okay, so even if we figure out this angle, we can find out the rest. So let's figure this out. So let's call this angle gamma. So gamma is, we have tan inverse of 3 over 2. So z would be, like this particular angle, let's call it theta, would be pi minus tan inverse of 3 by 2. Okay, so difference between greatest and smallest. So difference would be pi minus tan inverse of 3 by 2 minus pi by 2. So basically pi by 2 minus that. So pi divided by 2 minus tan inverse of 3 divided by 2. You are getting 0.588 radians. Now let's see this question. So the first and the second parts we can let go. Let's see this third one. This is similar to the one we just did, but with the real number now, real z now. So complex number is this, and on the diagram, on the sketch of an Argand diagram, shade the regions whose points represent a complex number z satisfying both the inequality z minus u is equal to 2 and real z greater than or equal to 2, and the u is basically this. So we can identify the shape now, right? So if we do z minus u equals to 2 is, we are not saying less than or equal to 2, we are saying this is a circle of center minus 1 minus root 3 and radius 2. Okay, so first off we have x and y axis, 1 2 1 2 3 4 1 2 3 4. Okay, and root 3 minus root 3 is roughly, now it's not going to be very accurate, so the center is at minus 1.7. so if for example we say this is minus 1 and let's say this is minus 2, so no, minus 2 over here, so 1.73 roughly right over here. So 1 minus 3, let's just gently make it over here. Okay, the radius is 2. That means the minimum point goes over at this side and at 3 over here. This is supposed to be a circle. We'll adjust the axes in a second. So roughly about this, right? And since, as you know, this, yes, so basically this is exactly how this would look like. And it may appear that it's passing through the origin, but it may not pass through the origin. May not. Okay, right. So basically this is somewhat, you can say like this. And less than equal to 2 means all of this region will be shaded. So consider this part to be shaded. Now we have real z greater than equal to 2. So that would mean x greater than equal to 2. So that was your x over here, real z greater than 2. So this would mean that we have a line like this. And greater than equal to 2 would mean that this part is satisfied. This means that only this part coincides to both of the regions. So, right. So this is the region. Now, what do we do further? What the question was? That's it? Whose points represent the complex number z satisfying both the inequalities. Right. So basically that's it. That's your answer. So you can say that this is your real z greater than equal to 2. So equals to 2 first. And this is your z minus u equals to 2. So this is the shaded part is your z. Right? Okay. Alright. Now another variation of this is when they, instead of argument, they're asking us about the mod z. Least value or greatest value of mod z. So we don't need the first part over here. The second part, look at it. Sketch the locus of the points representing complex number z satisfying the equation this. find the least value of mod z for the points on this locus. Okay, so this is also going to be very fairly easy. So this thing, z minus 3 minus 2i equals to 1. It is a circle of radius 1, center 3 minus 2. Okay, so let's gently just sketch this. Three minus 2. So 1, 2, 3. No, sorry, 1, 2, 3, and minus 2. 1, 2, 3, and 1, 2, minus 2. Let's scale it this way. The radius is 1, so it will come at minus 3 and minus 1 over here, and 4 over here, 2 over here. So that's going to be the radius. Okay, so let's adjust it now. So yeah, so somewhat like this, right? Okay, now find the least value of mod z for points on this locus. So the locus over here, like this, equals to 1 means this is just a circle. There is no region associated with it. Now least value of mod z means a point that comes from the origin directly on this path. So if you notice over here, this is not the least, this is not the least, the center is not the least, this point would be furthest away from it. So the least one would be right over here. So if I draw the sketch over here first, the guiding line over here, line that points to the center, but we are only considering this particular distance from origin to this particular point. Now how do we find out the least value of z? It's simple. We know the radius, this is 1. We know the distance to the distance from origin to center, 3 minus 2. This would be, just simply 3 squared plus 4 squared, 2 squared, 9 plus 4, 13. This is your root 30. So if the total distance from this to this is 13 and then you subtract 1, so least mod z would be root 13 minus 1. And that is the exact form. Similarly, had they asked for maximum of z, we would go up till this point. Straight line. We would go up till this point, and that would have been root 13 plus 1. Okay, so let's see this one. The shaded region on the Argand diagram shows the points representing the complex number z defined by two inequalities. The shaded region is bounded by a circle and a line parallel to the real axis. The boundaries of the region are included in the shaded region. Okay. Find two inequalities in terms of z that define the shaded region. Okay, so one of them is a circle, the other is a line. So line is pretty easy one. So this is your y is equal to minus 1. So this is going to be imaginary z less than equal to minus 1 because the region is below that. Now we need a circle. So the center of the circle is minus 2, 1 in Cartesian. And the radius is 1, 2, 3, right? So radius 3. So this would be just simply z minus 2 plus I equals to 3, which can be simplified as z plus 2 minus I. This is the circle, right? And the region is less than equal to 3 and imaginary z less than equal to -1. That's it. That's your two inequalities. Now find the greatest value of mod z for points in this region. So once again, mod z means length from origin. So we extend the lines from the origin and see where we are getting the maximum. So either it's this one, either it's this one, or maybe it's somewhere over here also. So this is an obvious one. We don't really need this. So this would be the minimum. Actually, no, sorry. This would be the minimum. This would be the minimum. And for the maximum, that would be the furthest away from that case. Okay. Now we just need to figure out the values where the circle crosses the -1, right? So we know the circle equation. That is x minus 2 plus 2, sorry, y minus 1 is equal to 9, and we need to find out where it is at -1. So x plus 2 whole squared plus -1 minus 1, that is -2 whole squared, that is just 4, equals to 9. So x plus 2 whole squared is equal to 5, which means that x plus 2 is equal to plus minus root 5. So therefore x would be right. So -2 plus minus root 5. We're clearly looking for this thing. So x value this -2 minus root 5. So therefore furthest point is equal to -2 minus root 5. So therefore the greatest argument would be, sorry, greatest mod z would be distance of z from this square of this plus -1 whole squared, that is 1's whole squared. So this is all we just need. So square root of square minus 1 minus 2 minus root 5 whole squared plus 1. So that's it. That's your answer. That would be how did we need it? Right, okay. Let's say let's try to find a more 4.35 would be the answer. Okay, 4.35. You can simplify this in the exact form also. If you do this in the exact form, this would be 4 plus 4 root 5 plus 5 plus 1. So you will get 10 plus 4 root 5 right. Okay. Alright, so now let's look at the second point that we listed over here, this thing. Okay, so this is also an easy one, so we'll do some practice questions for this also. Now, when you have z minus z1, we know it's the length of length from z1 to z. And we want this to be equal to length from another point. So basically what we're saying, length of, you can say distance of z from z1 and z2 are equal. In short, Z1 and Z2 are equidistant from Z. Z1 and Z2 are equidistant from Z. So when we want to be equidistant to 2 points, the locus of a certain point where you are equidistant from 2 points comes out to be a perpendicular bisector. Because not only at all times you are equidistant from the point, both of these points, Z1 and Z2, and this is also lies at the line which is perpendicular bisector of these 2 points. Alright, so this is easy one. Let's try out some questions for this, and we only have to use the simple coordinate geometry to find out the line, perpendicular line over here. You can find out the equation of the line using simple coordinate geometry and other conditions, right? So let's see some questions. Okay, so let's see this question now. So the A part is that. On a sketch of an Argand diagram, show the locus representing the complex numbers satisfying the equation mod z is equal to z minus 4 minus 3i. Okay, so we know what this is. So z, mod z basically means from the origin, and this is mod 4 plus 3i. Okay, so it's the perpendicular bisector between 0, 0 and 4, 3 basically. So we know that, and we'll have to sketch it also. So if we just gently sketch this, so this is your 0, 0, 4, 3 somewhere over here. If you know some constructions using the compass, etc., to draw the perpendicular bisector, that would be good. But at least if not, then try your best to have something realistic. Okay, so somewhat realistic. Okay, so let's see what equation do we get, because we will actually also need the equation because the locus of the complex numbers would be lying on a certain line. So yeah, okay. So first off, we have 2 points, 0, 0 and 4, 3, right? So first off, we find the gradient between them. Three by 4. Simple, 3 by 4. So that means the gradient of the line, which is perpendicular bisector, that would be bisector gradient would be minus 4 over 3. Okay. Furthermore, the midpoint where the perpendicular bisector is passing through is going to be, since 1 in the 0, 0, so 4 divided by 2 is 2 and 3 by 2. Okay, so now we can construct an equation: y minus y1 m x minus x1. So y minus 3 by 2, m is minus 4 over 3, x minus x1, which is 4. Sorry, no, 2, because it's passing through this. Right, so since you have 2 and 3, what you can do is multiply this entire equation by 6. You get 6y minus 9 equals to minus 8x and 16. Okay, so this would further be simplified to 6y equals to minus 8x and 16 plus 9, 25. So this is the line, and what we need is to just show the coordinate axis intercepts. So at y equal to 0, you have 8x equals to 25. So x would be 25 by 8. So 25 by 8, 3.125. And x, when x is equal to 0, 6y equals to 25. So y is 25 by 6. 25 divided by 6 is 4. I think we can leave it like that. 4.16 recording. Okay, so I think we can simply do that. So with this minor adjustment needed to the graph. Okay, so slightly over here, slightly over here. Mean point is 2, 3. 2, 3 by 2. Somewhat over here. Yeah, okay. So you can mark out the coordinate axes also. This is 25 by 6. This is 25 by 8. Okay, right. So locus is, you can say, locus is a line (6y equals to minus x plus 25). Alright. And what was the B part? Okay, find the complex number represented by the point on the locus where mod z is least. Alright, find the modulus and argument of this complex number, giving the argument correct to 2 decimal places. Okay, so where the mod z is least. So where the mod z is least is actually this point. Because both of these points, like the line is equidistant from z and this point 4, 3, and where the mod z is least is actually the midpoint. Okay, so we technically have already done that. The B part, we know that point, like the relevant point where mod of z is least, is minimum, is actually z is equal to this midpoint, 2 plus 3 by 2i. Now what we need is the modulus and argument of this complex number. Okay, so mod of z is going to be 2 squared plus 3 over 2 whole squared. So 4 plus 9 over 4. So 4 plus 9 divided by 4, that is 5 over 2. Okay, and the argument of z is going to be tan inverse of 1.5 over 2. 1.5 over 2 is basically like 3 by 4, so tan inverse of 3 by 4, this is the exact value, and in decimals this would be 0.644 radians. Okay, so we have both the exact value. Okay, so they asked us in the correct 2 decimal places, so this would be 64 radians. Right, okay, so that's it. Alright, let's see another question. Okay, so let's see this question. The complex number u is defined by u is equal to 4i over 1 minus root 3i. express u in the form of x plus iy. So this is easy thing. We just have to rationalize this first. So you have u is equal to 4i divided by 1 minus root 3i times by times by the conjugate of the denominator 1 plus root 3i divided by 1 plus root 3i. So 4i times by 1, 4i, and then 4i times by root 3. So plus 4 root 3i squared, so that would become minus 4 root 3 divided by 1, instead of minus root 3 iota squared, 1 plus 3. So basically divided by 4 you get I minus root 3. Okay. And next up was find the exact modulus and argument of u. Right, so modulus of u is 3 plus 1, so that is just 2. And the argument of u is 1 tan inverse of, it's basically in the second quadrant, right? So you can do pi minus tan inverse of 1 over root 3. So pi minus tan inverse of 1 divided by root 3 is 5 pi by 6, which is 150 degrees. Okay. On a sketch of an Argand diagram, shade the region whose points represent complex number z satisfying these two equations. Right. So what we do now, we know that this is a circle. You can write it as an equation also, but you can write it in words also. So this is, you don't need to write it. This is just what I am writing this for working. So this is a circle. This would correspond to a circle of radius 2, center 0, 0. And this would z minus, we have actually found that out, plus root 3 minus I less than mod of z is a perpendicular bisector between (0, 0) and minus root 3, 1. Right? Okay, so now let's draw that. So the scaling part has to be very uniform. Okay, so 1, 2, 1, 2, 1, 2, 1, and 2. So this is a circle. You have to draw this with a compass on your exam. So it would be better if you knew some constructions, like how to sketch perpendicular bisectors with compasses. So this is your minus 2, this is your 2, this is your 2, this is your minus 2, this is your origin. Alright, the other one was, the other point was minus root 3, so root 3 basically is minus 1.7. And this would be right somewhere, huh? Does it appear to be right over here? So just as a mental check, the circle is the equation x squared plus y squared is equal to 4. So the root 3 minus root 3 whole squared would be 3 plus 1 indeed 4. Yeah, so basically it is on the line. Okay, alright. So this is your that, and with a gray line we draw, actually with a dotted line we should draw. No, straight line. Okay, so this is your point, minus root 3 plus I, right? And this is 0, 0. Okay. The perpendicular bisector is going to go right in the middle. So it will be passing from this point. You see, it's a midpoint, right? So if this is 1, it's passing where? It's crossing 0.5. And it has to be perpendicular, so with a different color we'll do that. No, I think it's fine. Somewhat like this. Somewhat like this. So it appears to pass through 2. So we can actually verify that also, so that our sketch is relatively better. So you have 2 points, 0, 0. Very quickly, this working has to be very quick. Minus root 3 and 1. Gradient is 1 minus 0 and minus root 3 minus 1. So basically minus 1 over root 3. So gradient of the perpendicular bisector would be root 3, right? So simply root 3. And the midpoint would be minus root 3 over 2 and 1 over 2, right? So if you do y minus 1 over 2, root 3 x plus 3 over 2, and you multiply both sides by 2 very quickly, this would be 2y minus 1 equals 2 root 3x and then 3. Okay, so this would be 2y is equal to 2 root 3x plus 4. That means y-intercept is 2, right? So that part is correct, right? So it is passing from 2. But what about the x-intercept? Okay, even if like we show that this is fine, 2 points we have shown, but at x is equal to 0, at y is equal to 0, you have x is equal to 4 over 2 root 3, so that is 2 over root 3. Just like have, it would be better if we 1.15, so roughly, yes, so our value is not that far behind, so you can label it 2 over root 3, right? You can also label this point to be minus root 3 over 2, 1 over 2. Okay. You can label this point, right, midpoint. So this is a perpendicular bisector, that is the circle. Okay, now what did we actually need? Less than 2, less than that. Okay, and right, less than 2, less than that. Okay. So mod less than 2, mod z less than 2 means the entire circle, right? The everything inside the circle. That would be the mod z less than 2. But when you combine it with this means that it's closer to u than to z. So basically your region that you're actually highlighting would be this one. Alright? Now, it's not important to state this line over here. This is just for working. So at least your labeling and your graph actually looks right. Okay, so even if your scaling is a little bit different, even if you're not doing this by compass ruler, which is, I would definitely discourage doing that. Don't draw freehand. So if you're doing that, at least you should know the coordinate axes, the intercepts, coordinate axes, intercepts, wherever it's meeting. So at least that would aid in getting the rest of the marks. Right, okay. Now the third type of locus problem involves, that was the argument z minus z1 equals to some constant. Once again, this could be in the form of inequality also. So z minus z1, we have seen what that basically means. So argument, that would mean that you have z1, that your line is actually starting from z1. For example, if this is your z1, so if we give argument z minus 1, 2 equals to pi by 4. So basically means that if that z would be on this line if you extend it by pi by 4, in the pi by 4. So this is your pi by 4. Okay, so your line is originating from z1, this particular z1, and it goes in this particular direction. So in short, this is a half line originating at z1, particular z1, and it will have a specific gradient, and gradient equals to tan of the argument z minus z1, whatever is given to you. Okay, so if you want, if they ask you for a Cartesian equation, you can find that easily. Alright, so let's see some questions regarding this. Right, so let's see this one. On an Argand diagram, shade the region whose points represent complex numbers, z, which satisfy both the inequalities. See, once again, this is a circle. This is the half line that we were just discussing. So first we'll write them. This is for your working. So z minus 4 minus 3i less than equal to 2. Even equals to 2, you can do that. This is a circle, radius 2, and center 4, 3. Cartesian coordinates 4, 3. This one is a half line, so arg z minus 2 minus I. Even, let's say you do this with a pi by 3, it's a half line originating, or half line from 2, 1 in pi by 3 degrees. Pi by 3 radians, sorry. Okay, so that's how what we have to draw. So first I'll draw the half line first. So we have 4, 3, radius 2. So we have to be very, very careful with the scaling. 4, 3 is this. Okay, so that means we can bring it slightly over here. And 1, 2, this is your 4. 1, 2, this is your 4. This is 4, 3. This is your center of the circle. We have just marked it for a second. And you have 2, 1 right over here, the line. Okay? So first we draw the circle, radius 2. So this is going to be this, and this. Alright. So Once again, it's better if you do this with a compass in your own working. Right? Okay. So pi by 3 means 60 degrees. Okay, so this line is actually going 60 degrees. This particular line, this half line. So this 60 degrees line would actually be going slightly above 45. Right? So slightly above 45 degrees. This would be 45. So if it were 45, for example, if it were 45, if it was 45, then it would be passing right from over here. Okay, but since this is 60, it would be slightly over there. So pi by 3. So you can have this. So pi by 3. And this point is 2, 1. This is 4, 3. Okay. Now, what else do we need? Yes, certain labeling would be fine. This is 3, this is 2, this is 1, this is 4. Right? And this is 4, this is 2, this is 6. So we drew this line a little bit crude way, so you can find at least one more point over here. So you know the gradient of this line is tan of pi by 3. So tan of pi by 3 is root 3. Okay, so you can find out at least one more point. Okay, so let's say you have y minus 1, 4 minus 2 is equal to root 3. So 2 root 3 plus 1. So 2 root 3 plus 1 is 4.4. So roughly it's going 4.4. So over here, right over here. This will be the place that it's going. Okay, right. So yeah. Okay, now since we have spent a lot of time in sketching, we have to work with the the shading part. So this region less than 2 means this entire circle region, right? So you can draw that. You can write this. And argument z greater than pi by 3 means specifically which region? If we combine them, so wait, I'll stroke eraser. This. So this would mean specifically only this part. Actually, wait, let's go with a little bit smaller. Right, so basically this part. Now, the B part. Calculate the greatest value of argument z for points in this region. Okay? So argument z, once again, remember this is from the origin. So greatest value of argument z will actually come at this particular point. Okay? So this particular point. Right, okay, we can redraw this line. Right, never mind. Okay, so this is your line. Now we need this angle. Okay, So we need this angle. So what do we need about this? To find out this angle, we know that this point would be at 90 degrees to this line using simple circle theorems. And wait, use a dotted line, this, or gray line, for example, and this would be the distance to 4, 3. So we will be able to find the angle in parts. So first we'll find out this angle. Radius is known to be 2, right? And how about the other angle? So the other angle will be found by considering this particular triangle. So, the lower triangle, meaning this particular triangle, this particular angle, So the greatest value of arc Z will come from the standard. Right, okay. So greatest argument Z will come from this angle is 3/4, tan inverse of 3/4, right? Plus this angle, we need to know the length, 4 squared plus 3 squared d, 16 plus 9, 25, so that would be 5. So this length over here, this length is 5, right? So this particular length is 5. So if we need to find out this particular angle, we will do sine inverse of 2/5. Okay, we need, right, okay. So tan inverse of 3/4 plus sine inverse of 2/5, you get 1.06 radians. Alright, so since this wasn't exactly part of the part A, we have to erase these things. Oh, sorry, no. I'll erase the stroke eraser, right? This is gone, this is gone, and this, oh sorry, no. How do I, right, okay. Never mind. Okay, so even if that remains, that is fine. So this is your 4, 3. Right. Okay, so if I do this, right. Okay, so we can shade again, just because we need to keep this clean. So this would be, this was this particular region, right, and right. And even this one, you can erase that, right? You can instead keep a dotted line to show that. So, right, this and this, right. Otherwise, everything is done. So, that's it. Right, that's it. Now, let's try out 1 or 2 more questions. Okay, so let's see this question. On an Argand diagram, shade the region whose points represent complex numbers z satisfying these inequalities, right? So, these ones. So, this one is a perpendicular bisector between, so z minus 2I equals to, notice that I'm using equals to just to like describe the locus of the line, z plus 2 minus I, sorry. So perpendicular bisector of line joining (0, 2) and -2, 1. Okay, so signs are opposite. So 2i, that means 2y coordinate, -2 and +1. And the other one is, for example, the argument z plus 1 means line originating from 1, 0. Okay, 1, 0. Right. Okay. So let's try to do this. Okay. So there are 2 points, 2i. First, 2i. This is your 2i, and then you have -2, 1. So -2, 1 is right over here. Okay. You could go further up also. So let's say this is your 2, and this is your -2. So this would be the -2, 1. Okay. Then you have the line originating from 1, 0. 1, 0 means like this one. Okay, right. So if we join these 2 points, the perpendicular bisector is passing through like this. Okay, you can just quickly find out the midpoint, right? So midpoint passing through. So midpoint would be 0, -2, -1, and 2 plus 1, 3, 3/2. So notice that this is going exactly at that point. So this is your 1.5 and this is your -1. Right? Okay, so it's passing from the exact thing. And right, so I think this is fine, but if you want to be a little bit more thorough, then you can find out the y-intercept at least, because we have nailed down the 1 point. At least find out the y-intercept. Okay, you can do that, but that's not exactly necessary over here. But if we were to do that, so for example, let's say if we were to do that, we have 0, 2, and -2, 1, right? So gradient, sorry, what was I writing? So gradient is going to be 2 minus 1 and 0 minus -2. So this is 1 over 2. So m would be -2. So you have y minus 3/2 equals to -2 times by x plus 1. Okay, so multiply this entire equation by 2. You get 2y minus 3 equals to minus 4x minus 4. So you get 2y equals to minus 4x. Minus 4 plus 3 means minus 1. Right, so this would be means that it's passing through minus 1. Minus 1. So, wait a second. It's passing through this point, in fact. Sorry, no. This was 2 over here, so 1 over 2. I think this was correct before. So 1 over 2, right over here. Right over here. So y-intercept, what we made before was correct. Right, okay. So this is passing through minus 1 over 2. Right, okay. So yeah, so basically we have 2 points, then that means we have our line. Okay. Next up, that was the argument z plus 1, right? So between 0 and pi by 4. Sorry, once again, this is minus 1, 0, right? So z minus 1. So it's originating from right over here. So it's originating from over here, so it goes between 0 and pi by 4. So pi by 4 line will go from right over here. This is your half line. So the region between this is the region, and z minus 2i less than equal to 2 minus I. That means it's closer to this part. So I'll use a different color. No, different color. Yellow perhaps. So we are talking about this region. Okay. So this means that the area that coincides is only this part over here, right? Okay, so under the half line, so only this part, only this particular part, so not even this thing, right? So everything, I'll use a, right, so everything beyond this. Okay, so this part, this is your shaded region. Right? Okay. Okay. So that is, you can now label this also if you'd like. So this is your perpendicular. No, never mind. You can label the points. Minus 2, 1, or minus 2 plus I, that's however you want that. And this is your half line. This is your imaginary axis, this is your real axis. Right, okay, that's your locus graph. Okay. Alright, now let's see one last question. So on an Argand diagram, shade the region whose points represent the complex numbers z satisfying the equation. So inequality is this, from minus pi by 3 to this, and real z less than. Okay, so now this is easy. Half line starting from, so this point over here is 1 plus 2i. Right, so this is easy. So let's do this. So you have 1 plus 2i, so 1, 2. So the line is actually starting from this point. Okay. And 2, 3, 4, 5. And real z less than 3, this would be this particular line. Right over here. So once again, do this with a clean set of instruments, ruler, compass, whatever you need. The 1, 2 I from minus 60 degrees to positive 60 degrees. So this is going to go this way and this way. And it has to be a little bit identical. Okay, so it has to be a little bit identical, so we need to figure out at least the rate of change, right? So this is pi by 3, so tan pi by 3, I think we calculated over here, that is root 3, right? So tan inverse, so tan of pi by 3 is root 3. And root 3 is 1.7, so that means one unit change should get you 1.7 change. So, what we see over here, for example, 1 unit change, this is going to be 1.7. This is 3, this is 4. Right? So this is supposed to be 1.7111 right over here. Right over here. Okay? And this one also 1.7, so roughly like this. Okay, so this can go on. What I'll do is I'll copy everything. Nope. Below. This line continues above. This line goes this way. Okay, we could have actually drawn a shorter scaling also. However, it's fine. Okay, so how we actually did was, we need, in 1 unit, we need 1.7 fall, 1.7 unit fall, and 1.7 unit, right, so 3.7 roughly, 3.75, close to 3.75, and 3.7 fall. So somewhat like this, right? So we can erase this now. You can keep this one if you'd like. Right, so you can mark out this point. This is your pi by 3. And this is minus pi by 3. This is your point 1 plus 2i. And this is our line. Real z equals to 3. Okay. Now, real z less than 3, that means the region that we needed to shade less than equal to 3 was this one. Okay, this one. And in between this, in between this V diagram would have been this part. Okay, so that means it's in the region that satisfies both of them is actually in between this triangle, right? So what we just simply need is to simplify our shading. You can keep it as like a pencil shade also. Like obviously I have a highlighter over here, so I'm doing that with a highlighter, but you don't need a highlighter to do this. You can just use little pencil skills to do that, and up till over here. That's it. That's your shading. Okay, right, and that's about it. The last thing that you can do is to label the imaginary axis, real axis. Okay, right, and origin 1. The scaling needs to be a little bit precise. Right, okay. Now B part. Calculate the least value of argument z for points in the region from A. Least value of argument z, right. Give your answer in radians, correct to that. So the least value is actually coming from, once again it's argument z, that means from origin. So it's either this, right over here. Yeah, so that is the least point. No? That is the least point, argument z. Right, so we basically need to figure out where this point is. So one way to do that is to find the line of equation for this particular falling part, right? So we already have the gradient, so that m would be minus root 3, and it's passing from 1 comma 2, so y minus y1 equals to m x minus x1, so x minus 1, right? So this is your y equals to minus root 3x plus root 3 plus 2. Okay, now what we want over here is where x is equal to 3, right? So x is equal to 3. Minus root 3x. Right, okay. So x is equal to 3. This would be y minus 3 root 3 plus root 3 plus 2. So that is minus 2 root 3 plus 2. Okay. So minus 2 minus 2 root 3, that is this particular value, right? So y value over here at x is equal to 3. Actually, this is the entire part b that over here. So this is then continuing over here. Y is equal to 2 minus 2 root 3. Okay. So we have found the point over here. We have found the point over y value. The x distance we already have. So notice that we only need this particular angle. So we have this particular triangle. So tan inverse of, for example, this particular theta is going to be tan inverse of 2 minus 2 root 3 divided by 3. Okay, so tan inverse of 2 minus 2 root 3 divided by 3, and you get this value. Alright, so that was already in the negative now, so let's switch the signs a little bit. So minus, right. So this particular angle, the acute angle, is this particular part. So the argument z that corresponds to this thing is going to be negative. How much do we want it? In radians correct to 3 decimal places. So 0.454 radians. Right. So that's it for this complete topic. I hope you enjoyed doing these questions with me and learned how to do these questions also. If you have any confusions, doubts, or questions, feel free to reach out in the comments. If you felt that I was unable to explain a certain question, or if you'd like further explanation, feel free. Also, sign up for the May June 2026 preparation, either using the link given or through our Patreon. The membership is open for now. Until the next video, take care. Bye-bye.